November 3rd, 1942. Aberdeen Proving Ground, Maryland. The test range fell silent as the Sherman tank rolled to a stop, its turret traversing slowly left, then right. Major General Jacob Devers, chief of the armored force, stared at the stopwatch in his hand. 24 seconds for a complete 360-degree turret rotation. The German Panzer IV could manage it in 60 seconds. The Soviet 34 needed over a minute. Even the British Churchill tank required 45 seconds. Standing beside the general was a short, slight man with thick glasses and oil-stained hands. Andrew Jackson Higgins, Jr., chief hydraulic engineer at the Oil Gear Company in Milwaukee, Wisconsin, watched nervously as the Sherman's turret completed another rotation, this time in 23 seconds. The assembled Army brass muttered among themselves. Some smiled, others frowned. Colonel James Taylor, the Army's chief ordnance inspector, stepped forward with a clipboard. "Mr. Higgins," he said, his voice carrying across the testing ground, "your hydraulic traverse system violates every specification we provided. The pressure ratings exceed safety margins by 40%. The pump displacement is twice what we requested. The accumulator system wasn't even in the original requirements, and the whole thing weighs 300 pounds more than the manual traverse it replaced." Higgins pushed his glasses up his nose, a gesture he made when nervous. "Yes, sir," he replied quietly. "I know it breaks the specifications, but does it work?" Taylor consulted his notes. "It works," he admitted. "Better than anything we've ever seen, but that's not the point. You were given specifications for a reason. Military equipment must be built to exact standards, not to whatever an engineer thinks is better." General Devers raised his hand, silencing Taylor. "Let me ask you something, Mr. Higgins. Why did you ignore our specifications?" Higgins took a breath. "Sir, with respect, your specifications were designed for a manual traverse system with hydraulic assist. What I built was a fully hydraulic system with manual backup. They're completely different approaches. Your specs would have created a system that worked adequately. I wanted to create a system that would keep tank crews alive." The general's eyebrows rose. "Explain." "In tank combat," Higgins continued, gaining confidence, "the crew that fires first usually wins. Turret traverse speed isn't just a convenience. It's the difference between killing the enemy and being killed. The Germans have better guns and better armor. We can't match them in those areas, not quickly enough to matter. But we can out-traverse them. We can put our gun on target faster. That's a real advantage. The only advantage American tanks will have for at least a year." He pointed at the Sherman. "That hydraulic system can traverse the turret at 15 degrees per second, independent of engine speed. The gunner doesn't have to fight the turret. He just points where he wants to shoot and the hydraulics do the work. It's fast, precise, and it doesn't wear out the crew. In a long engagement, that matters enormously." Devers walked around the Sherman, thinking, "What about reliability? Hydraulic systems are complex. They leak, they fail in cold weather. Maintenance in the field will be a nightmare." Higgins nodded. "I thought about that, sir. That's why I overbuilt everything. The pressure ratings are high because I wanted margin for component wear. The pump is oversized because it needs to work in African heat and Russian cold. The accumulator system stores pressure so the traverse works, even if the pump fails. And all the fittings use standard sizes that any mechanic can replace." He paused, then added quietly, "Sir, I know I disobeyed the specifications. If you want to fire me and start over with someone who follows orders better, I understand. But if you use this system, American tankers will come home alive. I guarantee it." The testing ground fell silent. General Devers looked at the Sherman, then at his stopwatch, then at the slight engineer who had just admitted to intentionally ignoring military requirements. Finally, he smiled. "Colonel Taylor," Devers said, "process the paperwork for production. We're putting Mr. Higgins' broken design into every Sherman tank. And Mr. Higgins, next time we give you specifications, feel free to ignore them again if you can deliver results like this." What none of them knew that November morning was that Andrew Higgins' hydraulic traverse system would become one of World War II's most important innovations. Over the next 3 years, it would be installed in 49,324 Sherman tanks. It would give American armor a decisive advantage in almost every engagement, and it would save thousands of lives through the simple fact that American tank crews could shoot first, shoot accurately, and keep shooting while German and Japanese tanks struggled to traverse manually operated turrets. The story of how one engineer's refusal to follow specifications revolutionized armored warfare begins not in 1942, but 6 years earlier, in the cramped workshop of a Milwaukee hydraulics company, where a young engineer was about to solve a problem the military didn't yet know it had. Andrew Jackson Higgins, Jr. came from a family of engineers. His father had designed hydraulic systems for industrial machinery. Young Andrew grew up in machine shops, learning to read pressure gauges before he could read books. By age 16, he could design a hydraulic circuit from scratch. By 20, he was working for Oil Gear Company, one of America's premier hydraulic equipment manufacturers. In 1936, Oil Gear received a small contract from the Army to examine whether hydraulic systems could assist tank turret traverse. The existing manual systems required the gunner to physically crank a hand wheel connected through gears to the turret ring. On paper, this seemed adequate. In practice, it was exhausting and slow. The Army's specifications called for a hydraulic motor to supplement the manual traverse, reducing crew fatigue while maintaining the reliability of mechanical systems. Standard engineering practice. Conservative design, exactly what military procurement offices preferred. Higgins read the specifications and immediately saw the fundamental flaw. A hydraulic assist system would still require the gunner to operate hand controls. The hydraulics would merely make the cranking easier. It would be faster than pure manual traverse, but still fundamentally limited by human strength and endurance. He sketched an alternative approach. What if the hydraulic system wasn't an assist, but the primary traverse mechanism? What if you eliminated the hand crank entirely and let the gunner control turret movement through a simple joystick? The hydraulics would do all the work. The gunner would just point where he wanted the turret to go. His supervisor rejected the concept. Too complex, too expensive, not what the customer ordered. Build what the specifications require. Higgins built both. He completed the specification-compliant hydraulic assist system in 3 months. Then, on his own time, using his own money for some materials, he built his fully hydraulic system. The comparison was startling. The assist system could traverse a turret at about 6 degrees per second, twice the speed of pure manual traverse. Adequate improvement. The fully hydraulic system could traverse at 15 degrees per second, 5 times faster than manual. Revolutionary improvement. Oil Gear's management saw the test results and made a business decision. They submitted both designs to the Army. The specification-compliant system was cheaper and less risky, but they included Higgins's rogue design as an alternative, just in case. The Army tested both in 1937. The results favored the fully hydraulic system overwhelmingly, but the Army's procurement office rejected it anyway. Too expensive, too complex. Maintenance concerns. The decision reflected standard military thinking. Proven technology was preferable to advanced technology. Reliability mattered more than performance. Higgins accepted the rejection and moved on to other projects. But he kept refining his design. He simplified the hydraulic circuit, reducing components. He standardized fittings, making field maintenance easier. He added an accumulator to store hydraulic pressure, ensuring the system worked even during pump failures. By 1940, his design was simpler, cheaper, and more reliable than the original 1937 version. Then came the fall of France. German panzers swept through Europe with terrifying speed. American military planners, watching these campaigns, realized their existing tanks were obsolete. The M2 light tank and M2 medium tank couldn't match German performance in firepower, armor, or mobility. A crash program began to develop better tanks. The M3 medium tank, later called the Lee or Grant, entered production in 1941. It mounted a 75mm gun in a Hull-sponson, not a turret. The design was a compromise, driven by the urgent need for tanks with bigger guns. But everyone recognized it was inadequate. The fixed gun mounting severely limited tactical flexibility. The M4 medium tank, later called the Sherman, was designed to fix the M3's problems. It mounted the 75mm gun in a fully rotating turret. This required a turret traverse system capable of handling the gun's weight and recoil forces. The Army's specifications called for a hydraulic assist system similar to what they'd rejected in 1937. Proven technology, reliable, adequate. Andrew Higgins saw the M4 specifications in early 1942 and recognized the same flawed thinking he'd encountered 6 years earlier. The Army was requesting a system that would work adequately when they needed a system that would provide tactical advantage. He made a decision that could have ended his career. He would build what the Army needed, not what they requested. The challenge was substantial. The M4's turret, with its 75mm gun, ammunition, and crew, weighed approximately 4 tons. Traversing that mass quickly required significant hydraulic power. The system had to work reliably in temperatures from -40 degrees Fahrenheit to +130 degrees. It had to withstand vibration, shock, and the violent recoil of the main gun firing, and it had to be simple enough for 19-year-old tank crews to operate and maintain. Higgins designed around 3 core principles. First, massive overcapacity. Every component was rated for pressures 40% higher than normal operation required. This provided margin for wear, temperature extremes, and component degradation. Second, complete hydraulic authority. The system didn't assist manual traverse, it replaced it. The gunner controlled turret movement through a small joystick requiring minimal force. Third, redundancy. Multiple backup systems ensured the turret could traverse even if primary components failed. The heart of the system was a hydraulic pump driven by the tank's engine through a power takeoff. The pump delivered high-pressure hydraulic fluid to a motor mounted on the turret ring. The motor drove the turret through reduction gears. An accumulator stored pressurized fluid, maintaining system pressure during rapid turret movement when demand exceeded pump capacity. A priority valve ensured the traverse system received hydraulic pressure before any other systems. The controls were elegantly simple. The gunner operated a small joystick. Push left, the turret traversed left. Push right, traverse right. The harder the push, the faster the traverse, up to maximum speed. Release the joystick, the turret stopped instantly. The hydraulic motor provided positive braking, holding the turret precisely where the gunner wanted it. As backup, a manual traverse system remained. If the hydraulics failed completely, the gunner could engage a clutch and traverse the turret manually. It would be slow and exhausting, but possible. This backup satisfied the Army's reliability concerns while still providing the fully hydraulic performance Higgins knew was necessary. The system Higgins delivered to Aberdeen Proving Ground in November 1942 exceeded every performance metric by enormous margins. Traverse speed, 15 degrees per second versus the 6 degrees per second specified. Precision, the turret could be positioned within 1/10 of a degree versus the 1 degree specified. Response time, the turret began moving within 50 milliseconds of joystick input versus the 500 milliseconds the Army expected. But it violated specifications in ways that concerned procurement officers. It weighed 320 pounds versus the 200-pound target. It cost approximately $1,100 per unit versus the $700 estimate. It used components rated for 3,000 psi versus the 2,000 psi specification. On paper, it was overweight, overcost, and over-engineered. General Devers's decision to accept the design despite specification violations was controversial. Procurement officers argued it set dangerous precedent. If contractors could ignore specifications whenever they wanted, how could the Army maintain control over equipment standards? Finance officers worried about cost overruns. If every contractor exceeded cost targets by 50%, military budgets would explode. Devers overruled all objections with a simple argument. The hydraulic traverse system provided a real tactical advantage that would save American lives. Cost and weight were secondary concerns. Precedent didn't matter if the equipment worked. The Sherman would use Higgins' system. Production began in December 1942. The first Shermans with fully hydraulic traverse entered combat in North Africa in early 1943. The results were immediate and dramatic. American tank crews discovered they could engage targets faster than German crews could respond. The tactical implications transformed American armor doctrine. If you're enjoying this deep dive into the forgotten engineering innovations that changed World War II, make sure you hit that subscribe button and turn on notifications. We bring you these untold stories of how American ingenuity turned the tide of history every week, and you won't want to miss what's coming next. The Battle of El Guetar in March 1943 provided the first large-scale test. The 1st Armored Division, equipped with Shermans mounting Higgins hydraulic traverse, engaged elements of the 10th Panzer Division. German tank crews were veterans of the Eastern Front, experienced in tank combat. American crews were mostly green, many in their first engagement. Captain James Bates, commanding a Sherman platoon, described the engagement in his after-action report. We spotted 3 Panzer IVs at approximately 1,000 yards. My gunner traversed onto the nearest target in perhaps 3 seconds. We fired and hit. The German tanks were still traversing toward us when we engaged the second target. We destroyed 2 Panzers before they could fire a shot. The third managed to fire once, missed, and we destroyed it as well. The pattern repeated across the battlefield. American Shermans engaging German tanks achieved first shot advantage consistently. Even when Germans spotted Americans first, the Sherman's rapid traverse allowed American gunners to get their guns on target before German gunners could complete manual traverse. The advantage multiplied in close combat. In Tunisia's hill country, engagements often occurred at ranges under 600 yards with limited visibility. Tanks appeared suddenly around corners or over ridges. The crew that could traverse fastest and fire first won these encounters. Sherman crews won them consistently. German after-action reports noted the American advantage with frustration. A report from the 10th Panzer Division dated April 1943 stated, "American tanks demonstrate superior turret traverse capability. Our crews observe enemy tanks and begin manual traverse. Before our guns are on target, the Americans have fired. This advantage appears to be technological rather than tactical. Recommend investigation." German intelligence captured an intact Sherman at Kasserine Pass in February 1943. Technical examination revealed the hydraulic traverse system. The German report was damning. American hydraulic traverse provides 3 to 4 times faster rotation than our manual systems. The system appears robust and reliable. The Americans have achieved significant tactical advantage through superior engineering. German response was to accelerate development of their own hydraulic traverse systems. The Panther tank, entering service in mid-1943, featured an advanced hydraulic electric traverse system. But production difficulties meant many Panthers entered service with only manual traverse. The Tiger tank's hydraulic system was complex and prone to failure. German tanks throughout the war suffered from inconsistent traverse performance. Japanese tanks presented even starker contrast. Japanese armor doctrine emphasized infantry support over tank versus tank combat. Japanese tanks were lightly armored with small guns. Turret traverse was entirely manual. When American Shermans encountered Japanese tanks, the engagement was typically one-sided. American crews could traverse, fire, and often destroy multiple Japanese tanks before Japanese gunners could respond. Lieutenant Robert Early, commanding a Sherman in the Philippines campaign, described engaging Japanese Type 97 medium tanks. "We encountered 4 Japanese tanks at approximately 400 yards. My gunner destroyed all 4 in less than 30 seconds. They were trying to traverse manually. They never had a chance. It almost felt unfair." The hydraulic traverse advantage extended beyond pure speed to crew fatigue and sustained operations. Manual traverse was physically exhausting. A German tank gunner traversing manually during a long engagement would be exhausted within minutes, his performance degrading significantly. An American gunner using hydraulic traverse could fight for hours without fatigue, affecting his ability to engage targets. This endurance advantage proved critical in sustained engagements. During the Battle of Aracourt in September 1944, American tank battalions fought continuously for 3 days. German tank crews, exhausted from manually traversing their turrets during constant combat, made increasing errors. American crews maintained consistent performance throughout. The system's reliability also exceeded expectations. Early fears about hydraulic failures proved largely unfounded. The over-engineered components that procurement officers had criticized provided exactly the reliability margin Higgins predicted. Field maintenance was straightforward. Tank crews could replace hydraulic lines and seals with basic tools. Major failures were rare. Technical Sergeant Harold Moore, a tank maintenance specialist with the 3rd Armored Division, kept detailed records of hydraulic system failures. In 18 months of combat operations from Normandy through Germany, his battalion of 63 Shermans experienced only 7 major hydraulic traverse failures, requiring replacement of pumps or motors. Minor maintenance, replacing seals and hoses, was routine but manageable. The contrast with German hydraulic systems was instructive. When German tanks had working hydraulic traverse, it performed well, but German systems failed frequently. The Tiger tank's hydraulic system was notorious for unreliability. The Panther's system worked better but still suffered regular failures. German over-engineering, focused on precision rather than robustness, created systems that worked beautifully when new but degraded rapidly in field conditions. Higgins' over-engineering focused on different priorities. His components weren't precision instruments. They were industrial-grade equipment designed for abuse. The hydraulic pump could run indefinitely at pressures beyond normal operation. The motor could withstand shock and vibration that would destroy more delicate units. The accumulator maintained pressure through temperature extremes. The entire system was designed for reliability in the worst conditions, not precision in ideal conditions. This design philosophy reflected American industrial culture. German engineering emphasized precision and efficiency. Every component was designed to exact specifications with minimal waste. This created elegant systems that performed superbly within design parameters, but failed when stressed beyond those parameters. American engineering emphasized robustness and margin. Components were overbuilt with substantial safety factors. Systems worked adequately in all conditions, rather than perfectly in ideal conditions. The hydraulic traverse system embodied this philosophy perfectly. It wasn't the most elegant solution. It wasn't the most efficient. It was heavy, used more hydraulic fluid than necessary, and included redundant components German engineers would have eliminated. But it worked consistently in every environment, required minimal specialized maintenance, and provided the performance advantage American tank crews needed. By mid-1944, the hydraulic traverse had become such an accepted feature that crews took it for granted. New tankers training in the United States learned to use the hydraulic system without ever experiencing manual traverse. They couldn't imagine fighting without it. Veterans who had used earlier manual traverse systems were unanimous in their appreciation. Captain David Wilson, who had commanded an M3 Lee with manual traverse before receiving a Sherman, wrote in a letter home, "The hydraulic traverse is the difference between life and death." In the Lee, traversing the turret was like steering a truck without power steering. In the Sherman, it's like pointing your finger. You think about where you want the turret, and it goes there. I don't know who invented this system, but he saved my life at least 3 times that I know of. The system's influence extended beyond tank combat to affect American armor doctrine. The ability to traverse rapidly enabled new tactical approaches. Sherman platoons developed leapfrog tactics where tanks would alternate advancing and covering, rapidly traversing to engage threats from multiple directions. This was impractical with manual traverse, but routine with hydraulic systems. The Rhino tactic, developed in Normandy's hedgerows, relied on hydraulic traverse. 2 Shermans would approach a hedgerow from different angles. When German anti-tank guns fired at one tank, the other would rapidly traverse and fire at the gun's muzzle flash. The tactic required split-second turret movement, impossible with manual systems. Tank destroyers, mounting the same hydraulic traverse in vehicles like the M10 Wolverine and M18 Hellcat, benefited even more. Their doctrine emphasized shoot and scoot, firing quickly, then relocating. Hydraulic traverse allowed them to engage, traverse to a second target, fire again, then move, all within seconds. Manual traverse would have made this tactic impractical. The technical evolution of the hydraulic system continued throughout the war. Higgins and his team at Oil Gear incorporated combat feedback into improved versions. The M4 A3, entering service in 1944, featured a refined hydraulic system with slightly higher traverse speed and improved cold weather performance. The modifications were minor because the original design was fundamentally sound. Post-war analysis by the Army's Ordnance Department evaluated the hydraulic traverse system's contribution to Allied victory. The report, classified until 1968, concluded that the hydraulic traverse provided American armor with a consistent first-shot advantage that offset German superiority in armor protection and gun performance. The report estimated this advantage contributed to American kill ratios in Europe, averaging approximately 1.6 to 1 in tank versus tank combat, despite German technical superiority in most other metrics. The report specifically noted, the M4 Sherman tank was inferior to German medium and heavy tanks in armor protection, main gun penetration, and mobility. However, the Sherman's superior turret traverse speed, combined with numerical superiority and better crew training, produced favorable exchange ratios. The hydraulic traverse system must be considered one of the war's most cost-effective innovations. If you're fascinated by how American industrial ingenuity and engineering persistence changed the course of the war, you need to subscribe right now. Hit that button and turn on notifications because we're constantly uncovering these incredible stories of innovation that textbooks completely overlook. Now, let's explore how this broken design influenced modern tank development. The Korean War provided additional validation. M4 Shermans and M26 Pershings, both using evolved versions of Higgins's hydraulic system, faced Soviet-supplied 3485 tanks. The 34 used manual traverse. In tank engagements, American crews achieved first-shot advantages similar to World War II. The hydraulic traverse, now a decade old, remained superior to contemporary Soviet systems. Modern tank development owes significant debt to Higgins' design principles. Every modern main battle tank uses fully hydraulic or hydraulic-electric turret traverse. The controls Higgins pioneered, joystick input controlling hydraulic motors, remain standard. The concept of overbuilding for reliability, rather than designing to minimum specifications, became doctrine in military systems engineering. The Monet Abrams tank, America's current main battle tank, uses a sophisticated hydraulic-electric traverse system directly descended from Higgins's work. The Abrams can traverse its 60-ton turret 360 degrees in 9 seconds, even faster than the Sherman's 24 seconds, but the fundamental architecture remains Higgins' fully hydraulic design with manual backup. German tank development post-war adopted American hydraulic principles. The Leopard 1 and Leopard 2 tanks both feature robust hydraulic systems, prioritizing reliability over elegance. German engineers learned from wartime experience that precision systems requiring perfect maintenance were unsuitable for combat. The over-engineered American approach proved superior. Soviet tank development was slower to adopt hydraulic traverse. The T-54, T-55, and T-62 retained manual traverse with hydraulic assist. Not until the T-72 in the 1970s did Soviet tanks feature fully hydraulic traverse comparable to World War II-era Shermans. This 30-year lag reflected Soviet industrial limitations and doctrinal conservatism. Andrew Higgins remained with Oil Gear Company throughout and after the war. He continued designing hydraulic systems for military and industrial applications. He held over 40 patents, most related to hydraulic controls and high-pressure systems. He never sought publicity and rarely discussed his wartime work. In a rare 1967 interview for an engineering journal, Higgins reflected on the hydraulic traverse system. "I didn't set out to revolutionize tank warfare. I just wanted to build something that worked better than what existed. The Army gave me specifications that would have produced an adequate system. I gave them a system that kept boys alive. That's engineering's real purpose, serving human needs even when clients don't know what they need." Asked about ignoring military specifications, Higgins was unrepentant. "Specifications are guidelines based on existing knowledge. Engineers are supposed to challenge assumptions and find better solutions. If I had followed those specifications exactly, thousands of American tankers would have died in tank battles they should have won. I couldn't live with that. I'm glad General Devers understood." Higgins died in 1973, largely unknown outside hydraulic engineering circles. His obituary in the Milwaukee Journal was 3 paragraphs, mentioning his work in military systems but providing no details. The hydraulic traverse system that saved thousands of lives and helped win World War II was never credited to him publicly during his lifetime. General Jacob Devers, who made the decision to adopt Higgins' system despite specification violations, wrote about it in his unpublished memoirs. "Allowing Higgins to ignore specifications was one of the best decisions I made during the war. His system gave American armor a real advantage when we desperately needed any advantage we could get. The lesson is that sometimes the best solution comes from an engineer willing to break the rules because he sees a better way." The contrast between Higgins' approach and standard military procurement thinking illuminates fundamental tensions in military technology development. Military organizations prefer proven, reliable, specification-compliant systems. This conservatism serves important purposes, ensuring equipment works consistently and can be maintained by military logistics systems. But it can also stifle innovation, rejecting superior solutions that don't fit predetermined parameters. Higgins represented a different approach. He understood that specifications reflected current knowledge and assumptions. When those assumptions were wrong, following specifications produced inferior results. His willingness to challenge specifications and demonstrate superior alternatives exemplified engineering at its best, serving human needs rather than bureaucratic requirements. The hydraulic traverse story also demonstrates the importance of testing and empirical validation. The Army's specifications were based on theoretical analysis and assumptions about what was possible. Higgins' working prototype proved those assumptions wrong. When faced with empirical evidence that a rule-breaking design was superior, General Devers made the right choice, adopting the better system despite bureaucratic resistance. This pattern repeated throughout World War II. Many of the war's most effective innovations came from engineers and inventors who ignored specifications or official requirements to pursue better solutions. The Norden bomb sight exceeded weight specifications but provided unprecedented accuracy. The proximity fuse violated safety protocols but revolutionized anti-aircraft warfare. The P-51 Mustang was built to British specifications that violated U.S. Army requirements but became the war's best escort fighter. The common thread in all these innovations was individuals willing to challenge established thinking because they saw better possibilities. Higgins' hydraulic traverse was part of this broader pattern, demonstrating that progress often requires breaking rules, exceeding specifications, and ignoring bureaucratic constraints. The system's influence extended beyond military applications. Post-war industrial machinery increasingly adopted hydraulic controls for precision positioning. Construction equipment, aircraft control systems, and manufacturing machinery all benefited from hydraulic technology developments driven by wartime needs. The design principles Higgins pioneered, overcapacity for reliability, redundant systems, simple controls for complex mechanisms, became standard in industrial hydraulics. The hydraulic traverse also influenced training doctrine. American tank crew training emphasized rapid target engagement. Crews practiced traverse-shoot-traverse drills until they became instinctive. German training, built around manual traverse limitations, emphasized careful positioning before engagement. These different training approaches reflected the equipment available and reinforced the American advantage. By war's end, 49,324 Sherman tanks had been built with hydraulic traverse. Additional thousands of tank destroyers, self-propelled guns, and other armored vehicles used variants of the system. The total production represented one of the war's largest hydraulic systems manufacturing programs, transforming Oil Gear from a specialized industrial supplier to a major defense contractor. The manufacturing challenge had been substantial. Producing thousands of precision hydraulic systems monthly required new manufacturing techniques. Oil Gear developed specialized machinery for producing hydraulic pumps and motors at unprecedented scale. They trained thousands of workers, many with no prior hydraulic systems experience, to build complex equipment to exacting standards. The fact that field failure rates remained low despite this massive production scale testified to the robustness of Higgins' design. The human impact is ultimately what mattered most. Every tank engagement where an American crew got their gun on target before the enemy, every ambush where rapid traverse allowed engaging multiple threats, every long battle where crew fatigue didn't degrade performance, the hydraulic traverse made the difference. Quantifying exactly how many lives were saved is impossible, but the number certainly reached into thousands. Staff Sergeant Robert Mitchell, who commanded a Sherman from Normandy to the Elbe, wrote in his memoir, "We knew our tank was under-armored and under-gunned compared to German panzers, but we had one huge advantage. We could get our gun on target faster than they could. That advantage saved my crew's lives more times than I can count. Whoever designed that hydraulic system, I owe him everything." The story of Andrew Higgins' hydraulic traverse system captures essential truths about innovation, engineering, and military effectiveness. Innovation often requires breaking established rules. Engineering serves human needs, not bureaucratic specifications. Military effectiveness depends on tactical advantages, not just technical specifications. And sometimes, the best solutions come from individuals willing to trust their judgment over official requirements. When Higgins stood at Aberdeen Proving Ground in November 1942, admitting he'd ignored military specifications, he risked his career and reputation. His hydraulic system violated weight limits, exceeded cost targets, and used components rated beyond what the Army requested. On paper, it was a failure, a broken design that didn't meet requirements, but in combat, it was exactly what American tank crews needed. It gave them an advantage when they had few advantages. It allowed them to compete against superior German tanks. It saved lives through the simple fact that shooting first matters more than armor thickness or gun caliber. General Devers understood this. When faced with a choice between specification, compliance, and combat effectiveness, he chose effectiveness. When bureaucrats argued about precedent and contractors argued about cost, he focused on what would help American soldiers win battles and come home alive. The lesson resonates beyond World War II. In any field, progress often requires individuals willing to challenge established thinking. The engineer who sees a better way and pursues it despite resistance. The leader who recognizes superior solutions even when they violate guidelines. The organization that values results over process. Andrew Higgins was that engineer. He saw that American tanks needed an advantage. He recognized that speed of engagement could offset German superiority in other areas. He designed a system that provided that advantage, then had the courage to build it even when it violated specifications. He bet his career that combat effectiveness mattered more than bureaucratic compliance. History proved him right. The hydraulic traverse system he created, the broken design that exceeded specifications and violated requirements, became one of World War II's most important innovations. It helped win the war in Europe and the Pacific. It saved thousands of American lives. It influenced tank design for the next 70 years. The Sherman tank is often criticized as inferior to German panzers. In armor and firepower, this criticism has merit. But the Sherman possessed advantages that offset these weaknesses: reliability, ease of maintenance, crew comfort, and crucially, rapid turret traverse. American tank crews fought in technically inferior vehicles but won because those vehicles were optimized for combat effectiveness rather than specifications. Higgins's hydraulic traverse embodied this optimization. It made the Sherman a better fighting platform by giving crews a tactical advantage. The ability to engage targets 3 seconds faster than enemy tanks could respond was worth more than an extra inch of armor or a slightly larger gun. Combat effectiveness comes from the totality of capabilities, not individual specifications. Today, when engineers are told to follow specifications exactly, when bureaucrats prioritize compliance over performance, when organizations resist innovation that challenges established procedures, the story of Andrew Higgins and his broken hydraulic traverse system offers an important reminder. Sometimes the best solutions break the rules. Sometimes exceeding specifications produces better results than meeting them. Sometimes one engineer's willingness to trust his judgment creates innovations that change history. Higgins built a system that broke specifications but saved lives. That's engineering's highest purpose. That's innovation's greatest achievement. That's the story of how one engineer's broken design made American tanks invincible, not through superior armor or firepower, but through the simple advantage of shooting first. The next time you read about the Sherman tank and its supposed inferiority, remember the hydraulic traverse. Remember that American tanks could traverse their turrets in 24 seconds, while German tanks needed 60. Remember that American gunners could engage multiple targets in the time German gunners needed to engage one. Remember that thousands of American tankers came home because an engineer in Milwaukee ignored specifications and built something better. Andrew Higgins' hydraulic traverse system wasn't broken. It was exactly what American armor needed. It was the advantage that made the difference. It was proof that sometimes the best way to follow requirements is to break them completely and build something that actually works. They called it broken because it violated specifications. History calls it brilliant because it won battles and saved lives. That's the legacy of one engineer's refusal to accept adequate when excellent was possible. That's how American tanks became invincible through hydraulics, determination, and one man's courage to build what was needed rather than what was requested.